Welcome everyone. Today we're very happy to have Francis Xu, who will tell us about the game of cycles. Oh, and how would you like people to ask questions if they have any?
The chat would be fine, or I mean, if people want to raise their hand, that's also fine too.
Okay. Yeah, go ahead.
All right, great. Well, welcome. It's fun to be with you all, and certainly the wonders of technology make it even easier to do something like this. I would love to tell you about a game that I started playing and have studied with a number of different people, collaborators, who I'll tell you a little bit about. One of them is a incarcerated man named Christopher Jackson, with whom I started a correspondence, a long correspondence, over many years. And one of the ways that we engaged with each other in chatting about our mutual interest in mathematics is by playing this game and beginning to study it as a source of interesting questions. And then at some point, we brought in some other mathematicians who are all professors at various schools. I teach at Harvey Mudd College, which is a small science and engineering school in Southern California. And these are my collaborators who are spread across the country at various institutions. We all met at a summer institute called ICERM, which is at Brown University. And this was a research project that we worked on for most of the week that we were there. This game is a game that I mentioned, developed partly because I was interested in putting a new puzzle in my book, Mathematics for Human Flourishing, which is really not a book of puzzles. It's more about a book about what it means to be a human being and using math as a lens. But in between each chapter, I have some puzzles to engage the reader. And one of them was this game. And as a result of playing the game, there are some natural questions that arise. Okay, so let me see if I can tell you what the game is, and then I'll have you investigate a little bit. So the board of the game is any planar graph. So you can think of a graph as just a collection of dots and edges. I think we got somebody who needs to might want to mute. Thank you. Okay, great. So any collection of dots and edges is a board. All right, and whenever you draw a diagram of dots and edges, it divides the plane into what we'll call cells. So the bounded regions here are cells. This particular board that I'm pointing at right now with my cursor has 3 cells. Okay, we're not thinking of the outside as a cell. We're just thinking about the insides of cells. Although you certainly could later on, if you want to generalize this, think about it that way. Here is another board that has 1, 2, 3, 4, 5, 6 cells. Okay. And now this is a 2-player game. Each person takes turns marking an edge with an arrow, which you have 2 choices. You can mark it going one way or the other way. All right. Okay, what else? Well, the goal of the game is to produce a cycle cell. So this is an example of a board that has several edges marked, and you notice in red, there is a collection of edges that all cycle in one direction around a single cell. Okay, so that's a cycle cell. It's a single cell, I should point out. Notice that this, if you follow my arrow, my cursor around these 2 cells, it also cycles in one direction, in this case clockwise, around 2 cells, but that doesn't count because it's not a single cell. We're interested in a single cell that is surrounded by either clockwise or counterclockwise circling thing. Someone just asked, do I have an interactive version of the game? No, but if somebody wants to code up an interactive version, that'd be wonderful. Okay, now there is so that you either want to get a cycle cell, or it's possible, maybe you're done at the end, you won't be able to make any moves and nobody's made a cycle cell, then the last player to play wins the game. Okay, All right, now there's a rule that makes this, is the thing that makes the game interesting, is you aren't allowed to create any sinks or sources. So a sink is a dot with all the edges marked in. The source is a dot that's all the edges marked out. And you're not allowed to do that. Okay. So great. So yeah, so let's think about, let's play the game. Okay, so how would we play the game here? So, okay, so well, I guess we could just, for instance, player one. Okay, so I'll be player one. Okay, and maybe someone here, a volunteer, would like to be player two. Anybody want to be my volunteer? Don't worry, you won't really be doing anything. I'll be making all the moves. Okay, is it Samvar? Okay, so here we go. Player one. Sure. What's that? Did I say your name correctly?
Yeah.
Okay, Samvar. Okay, great. So do you want to be player one or player two?
I can be player one or player two. It doesn't matter. I'll be player two.
Okay, you be player two. Okay, I'm player one. And I just made this move on this board. And player, where would you like to move?
I'll take the center one.
Okay, there is a center dot and several edges from the center.
Center vertically upwards.
Vertically upwards. Okay, great. I just made you think you had choice, but you actually don't. Okay, so here's a move that you might make, a second move. Now, if you made this move, would you agree this is a stupid move to make? Let's see. Why is it a silly move? Well, it's a silly move because if I'm trying to create, we're trying to create a cycle cell and you just put another edge here, then I could just finish by playing that move. Does that make sense?
Yeah.
So you probably don't want to make the second to last arrow on a cycle. Okay, so that's what we'll call a death move. All right. Okay, so not a good move. So suppose you choose to make another move. So here's a move you might choose to make. You might choose to go the other direction. Okay. Does everybody agree this is a legal move to make? Okay. It has not created a source or a sink. Notice that here at this corner, bottom right corner, this does now restrict what's going to happen on the bottom edge now, because you'll see now that if Samvar made this second move, this bottom edge is now what I would call unplayable. Why? Because if I mark it going to the left, it creates a source here, yes? And if I mark it going to the right,
then I can complete a cycle.
Exactly, it's a death move. Okay, everybody happy with that? It's not a good move to make for me. Okay, so I'm gonna make a different move. I'll make this one. Now, the interesting thing that happens is because when I make this move, would you agree that Samvar now can play this edge? Because the death move is no longer a death move. If Samvar plays it going left, that's not legal because of the source rule, but Samvar can play it going right. Are you with me?
I think that would be the best move.
You do? Okay.
Yeah.
Okay, yeah. Unfortunately, it's not the move I had you making. Okay, but suppose you made this move now. Do you agree that do all of you agree that if Samvar makes this move, this bottom edge is now unmarkable, which means it is now forever not a playable move, because marking to the right or to the left produces a source either at one of these two corners. Everybody happy with that?
Yeah.
Okay, good. And so now, so Leo asked, couldn't you go from center dot to top dot for move 4, resulting in a guaranteed win? Center dot to top dot would actually be a death move. Yeah, but yeah, thank you. Yes, because of that edge is no longer there. But yes, there are other ways to play this game. But do you agree now that in fact this game now has no move for me if I'm the next player? Sambar made this move. If I point it up, I create a sink. If I point it down, I create a sink. Okay, so this is now both edges are unmarkable and the game ends. Are you with me? And who wins?
So is this game a tie, or does the person who cannot make a move lose the game?
The one who can't make the moves loses. The last person to make a valid move wins. So you win this game. Okay, so Sambar wins. Are you with me? Everybody understand the game?
Yeah.
Certainly Benjamin does, because I see Benjamin's smiling, nodding face. Thank you. Okay, great. So here are some things to notice that we just noticed. Death move is marking the second to last edge of a cycle. It's currently unplayable edges can become playable, but unmarkable edges stay unmarkable. Okay, those are some terms we'll use. Thank you, Matthew and Suma. Good to see you. All right, so what are some questions you might ask of this game? Well, a natural question to ask is, which player has a winning strategy, right? And can you easily describe that strategy? Now, here's another question that we asked, that after playing the game a bazillion times, we realized something interesting, that it seemed that every time we played a game to the end, if we played the game so that every edge gets marked, it always seemed that there had to be a cycle cell. Like it seemed we never encountered a situation where you could mark every edge and not have a cycle cell. And so that was an interesting question we also wondered. So these are the two questions I'm going to try to answer during this this talk. Okay, so good. So if we're going to begin to study the game, where would you like to start? Let's see. Well, probably want to choose the simplest board possible. That might be a good place to figure out what happens. So here's a board that we thought. Let's just choose a board with a single cell. So this is a polygon with edges around it. Okay. And it turns out, of course, this is a very simple game. And the only way you can win is either creating a cycle going all the way around, or because the other person's naturally going to try to block you, but you basically want to make the last move. Okay. And it turns out that the parity, the evenness or oddness of the number of edges, is all that guarantees who wins. It's actually actually a brainless game. The winning person who has a winning strategy doesn't even have to think. Okay, so why? So what happens? Well, the claim is that if the n is odd, then player one wins, and if n is even, player two wins. So here's a octagon. The claim is player two will win, and it's unavoidable. Player two is going to win no matter what moves the player makes. Okay, why? Well, the reason is, for instance, do you see in this current configuration of the game that this edge is unmarkable? Because pointing to the right turns this into a sink, pointing to the left turns this into a sink. Yes? Do you agree that this edge is markable? It's markable in only one way. You cannot have it pointing down because that turns this into a source, but you can have it marked pointing up. And the reason you can mark it is because this edge is also is not currently marked. So if you play the game to its completion, you will naturally end the game with unmarkable edges being the only edges that don't have marks, right? And those edges are going to be ones where that they'll have, the claim is they have to come in pairs. Why? Well, basically what's going to happen is you'll have some edges going clockwise, some edges going counterclockwise, and the only edges that are not marked are ones that are single edges. And so if you go clockwise some of the time and counterclockwise some of the time, you have to come back to clockwise when you eventually go all the way around the circle. So the number of edges that are not marked has to be even. So if the number of unmarked edges is even, and you have an even number of edges total, that means there's an even number of edges that were marked. So player 2 was the one who made the last play. Okay, that's the basic idea of this game. It's very simple, single cell boards, we know who wins. All right, everybody happy with that? Okay, great. I see a question here about a different kind of game. That's a different game. We have not considered that game. It might be an interesting game. The question was, what if you had a different win condition? Yeah, we'll talk about that at the end of the talk. Okay, so what about a more interesting game? Here's a more interesting game, and I don't have an interactive version. But just for fun, I'm gonna pretend that Benjamin is my player. Benjamin, do you want to be player 1 or player 2 for this board? It's a more interesting board than.
I can be player 2.
You'll be player 2. Okay. Actually, I should be player 2 if that's okay.
All right, I'll be player 1 then.
Okay. Yes, because this board is not interactive. So Benjamin is going to play, and let's suppose Benjamin makes this move. Now, unbeknownst to you, I have a strategy for playing this game, and let's see if you can figure it out. Okay, here we go. Benjamin makes this move, and I make this move. Okay, now, watch closely, and when you think you know my strategy and you're willing to guess what my strategy is, raise your hand. Okay. Now Benjamin makes this move, and I make this move. All right. Benjamin makes this move, and I make this move. I'll wait till at least 2 other people have their hands up. Benjamin makes this move, and who's willing to tell me what the next move is going to be? I'm waiting for one more hand. Okay, thank you. Eugenie, what would you say?
The top left above. Yeah.
Oh, okay, top left going up. Okay, thank you, Samvar, for suggesting it. So you suggest top left going up, yes? Okay, great. So what is that strategy? Can you vocalize what that strategy is? And I'm gonna try to let Eugenie talk this time. Okay, so let's Eugenie, what was the strategy you had in mind?
I guess you mirror what he's doing.
Yeah.
Like on the other half.
Okay, it's mirroring, but how did you decide whether it was up or down?
It's in the same direction as his arrow.
Oh, okay. Okay, interesting. Okay, good. So so this board, so what made this strategy possible is that this board had a certain symmetry, didn't it? Like there was something that was directly across. So that's a 180-degree symmetry. So if I turn this board 180 degrees, would you agree that this edge turns into this edge? Yes. And what Eugenie is noticing is that if this edge is turned 180 degrees, this arrow would actually be pointing down, but Eugenie's making the choice to have it point up, which sort of looks like the direction that it came from, but the symmetry would not have done that. So we have to reverse the edge. That's the symmetric opposite. Okay, so that's what we're doing. And now, what about this move? What should I do after this move? What should you do after this move? You're player 2.
Like I guess the edge that's right below it.
Yeah, you could do that, but
it's the same. Oh wait, you can't do the same move though.
You could do that, but that would maybe not be the wisest move to make, because does anybody see another move that might be better? Yeah, complete the cycle. So do you agree that if I were player 2, or I guess if I were player 2, I'd try to complete the cycle whenever possible. Okay, this is a death move for player one. Okay, so Benjamin should be doing this move next. Okay, everybody happy with that? Okay, so what's the strategy? This is what's going to work for symmetric boards. The strategy is to basically do the mirror and then reverse the edge. Okay, so what I'm suggesting here is actually going to work for boards that have what we call involutive symmetry. Every edge has a partner, and it could happen because of 180-degree symmetry, but it could also happen because of reflection. Okay, so reflective symmetry, 180-degree rotations, they're examples of what we call involutive symmetry. Every edge has a partner, and we're doing what we call mirror reverse strategy. Okay, so this is what we learned for 180-degree symmetry. So the question you might ask yourself is this strategy always going to work? Right? If Benjamin plays Eugenie's strategy, is Benjamin always going to have a move to make? How do we know that Benjamin's move doesn't result in a death move? That's another bad thing, right? How do we know that Benjamin move's not going to create a source or a sink? Do you agree that those are the kinds of things we worry about with this strategy? Like, it seems like it's going to work, but how do you know? That's where we have to prove some things, right? So this is what we're able to prove. It doesn't always work for every symmetric board, but here's what we know. For a board with 180-degree symmetry where no edge and its distinct partner are part of the same cell, we can say something. If there's no edge through the board center, player two wins. And if there's one edge through the board center, player one has a winning strategy. Okay, so here's an example of a board that has 180-degree symmetry. So a 180-degree symmetry here is a symmetry. Yeah, you reverse it 180 degrees. Do you see that if I turn this thing 180 degrees, it stays the same? Similarly, that's true here. It stays the same. Notice here that every edge has a distinct partner. Here, this edge is its own partner. When you turn it around, this edge stays the same. So in this case, there's no edge through the board center. Player two has a winning strategy just by mirror reversing. So if I play something, Benjamin has a move to make. Yes? In this case, if player one has a winning strategy, I would win by making the first move on this edge that passes through the board center. And then no matter what Benjamin does next, I will mirror reverse whatever Benjamin does. That's the claim that will always work. I haven't proved it, but that's the claim. Okay. On the right side is a picture of a board for which this strategy will not work. And the reason here is that, do you see that if, let's say, I make this move, Benjamin makes this move, and I make this move, and Benjamin makes this move, and I make this move, notice that Benjamin will make this move, and I could just win because Benjamin just was forced into making a death move. Because we just went around the cycle, all but one edge, and now I could finish. So mirror reversing doesn't work here because this edge and this edge were part of the same cell. Okay, so that's the claim, is that this strategy doesn't work in this case. It doesn't mean that some other strategy could work. That's just talking about this particular strategy. Okay, that's what we know, and now you have to convince yourself why it works. But I'll come through. Well, maybe I'll talk through it now, and then you'll see later. Okay, so why does this strategy result? Okay, so here's a question. If I make a move and then Benjamin makes a move, why is Benjamin's move always available to make? Anybody see why? That if I perform the mirror reverse strategy, or Benjamin does, why is the move always available to make? I want to hear from someone I haven't heard from yet. Let's see. Well, if Benjamin's move were already taken, it would have been taken by So why would it be taken? It would be taken because either person made the move already, somebody already made that move, and either that was Benjamin on a previous move. It wouldn't have been though, because Benjamin's only responding to what I do, or it would have been me on a previous move. But if I did this, Benjamin would have made the move I just made. So the move is still going to be available. Okay, so that's the argument. That's one way to think through that argument. Now, the other question is, how do I know Benjamin's move isn't going to create a source or a sink? Anybody see why? If I make this top move and Benjamin makes this move, how do I know Benjamin's move is not going to create a source or a sink?
Then the only way that I guess my strategy, the mirror reverse strategy, would make a source or sink is if the other person made a source or a sink.
First, yes, good. If there had been a source here, for instance, that would have been because because my move had created a sink in the other situation because of the mirror reversing. So that's why. And then of course, how do I know it's not a death move? I don't, unless I'm guaranteed that the move isn't going to contribute to something on the same cell. That's the basic argument. Now, of course, when you're listening to math talks, you're like, maybe it's not possible to follow everything so quickly, but you're just listening for the big ideas, right? And you can maybe work out the details if you think about it closer. Now, for reflective symmetry, you could ask, what happens, right? This is symmetry that involves a reflection. And for a board with reflective symmetry and no edges along the axis. So here's the axis of symmetry, vertical. If there's no edges along the axis, the mirror reverse strategy works. Again, if no edge crosses the axis, basically, if there's an even number of edges, player 2 wins. And if there's an odd number of edges, player 1 wins, but there has to be only one edge crossing. Okay. So and the strategy is the same. If player 1 has a winning strategy, they play that one edge that crosses the axis. And then player 1 will just mirror reverse anything that the second player does. Here, the second player mirror reverses anything the first player does. Now, the reason why this creature fails is because doing mirror reversing may not be a valid strategy. So just to give you an example, player 1 marks this going up, and player 2 then marks this going up. Mirror reversing would say player 3 should mark this going down, but that's a death move player for the first player, where it wasn't a death move for the second. So that's one of the issues that can happen. And okay, so I'll have you notice that these theorems don't say anything about what happens if you have multiple edges crossing this axis. Okay, so we don't know what happens there in general. And here are the three things I've already talked about that you have to think about when you want to prove whether this strategy works. Okay, and so there is a more general theorem we're able to prove. Like after proving both these things for symmetric boards, we're like, oh, maybe this is actually an instance of the same one theorem. Okay, so here's the way we thought about it. If you have a cell that's its own partner, so what do I mean? Notice that this cell, when you do this is 180-degree symmetry. When you do the symmetry, the cell gets sent to itself. We'll call that self-involutive. We'll call a cell nowhere involutive, like this one, if when you reverse it, when you do the symmetry, it goes to a completely different cell and no edge has a partner in its cell. And it's part involutive, like this one, if the cell itself is not self-involutive because it goes to a different cell, but one of the edges gets sent to another edge in the same cell. It's the third situation we want to avoid. And so mirror reverse strategy works for any involutive board, such that each cell is either self-involutive or nowhere involutive. And if there's no self-involutive edge, player 2 has a winning strategy. Player 1, if there's one self-involutive edge whose vertices aren't fixed by the involution, then player 1 has a winning strategy. Okay. Oh, okay. So maybe the theorem's slightly misworded here. What I'm saying is mirror reverse strategy could work. And if there's no self-involutive or one self-involutive, we know what happens. If it's more than one self-involutive edge, we don't, this theorem doesn't say anything.
It's time to go
Okay.
to a
Hang on one
separate
sec.
breakout room. So
Sorry, that's my class that's still a meeting in the other Zoom room. Okay, here we go. So great. So let me address the second question that I asked, which was, is it possible to fill out a board where every edge is marked and no sources have a cycle cell? And the conjecture was, in fact, yes. And here's one way you might think about this question. So it's basically saying if you have a city with all one-way streets, every edge is marked every street is marked one way. And if there's no stupid intersections, what I mean by that, what I mean is if there's no sinks, that is, you don't want an intersection where all the traffic flows into that and there's no way to leave, right? That would be a stupid intersection. Another stupid intersection would be you have an intersection where all the traffic flows away, but you could never get there. Okay. So here's the question. Is it true that if you take a city with one and you mark every edge as one way with no stupid intersections, must there be a single block around which the traffic cycles? What do you think? If you want to, I'd like to see everyone vote if you can. Vote on this question. If you think the answer is yes, you must have a reaction that says, allows you to answer yes. And if you think the answer is no, mark no. Just go ahead and vote. Tell me what you think. The answer is. I want everybody to form an opinion. I know some of you are like, I don't know. Well, of course you don't know, but see what you think. Do you think the answer is yes or no? I mean, we certainly thought the answer was yes. And so the question is, do you think we were right? Or do you think there was perhaps some case we hadn't thought of? See, everyone who's voting is voting yes. Interesting. Okay, thank you, Simon, for taking the opposing view. Certainly something weird could have happened, couldn't it? Yes? So here's interesting. Let's look at this example. So I filled out this board with one-way streets. And do you find a cycle cell in here? Yes, you do. Yes? Okay. But now let's just observe what happens if we try to tinker with this. Suppose I take this edge and I reverse it. If I reverse it, this is no longer a cycle cell, is it? But is there another cycle cell when I do that? Yes, this one right here. So somehow I could not modify this edge and still keep it a cycle cell. What if I turned this one, reverse this one instead? Is there another cycle cell? Yes, at the top. Oh, okay. Well, wait a minute. What about this edge? Suppose I reverse this edge and make it point up. Oh, it creates a source. Oh, huh. So no matter how hard I tried here, I could not tinker with this to get it to not have a cycle cell. Huh, interesting. Okay, so interesting. So it turns out that this conjecture is true, and it's an example of what I would call an existence proof. And here's a way. I'm just going to flash some pictures at you because I won't be able to technically go through this carefully. But it turns out that this is true. And here's the strategy we used. Okay, so if you think about a city with one-way streets, if the city's just got a finite number of intersections, you could just follow the flow of traffic. And if you followed the flow of traffic, would you agree that if you followed the flow of traffic, if at every intersection you just chose one out direction, so every intersection has at least one in direction and one out direction. So if at every intersection you chose, maybe it has multiple out directions, just pick one. And then you fix that. Now, if you follow the flow of traffic through the chosen out directions, you have to cycle at some point. That's because there's only finitely many places to visit in the city, okay? So that produces a cycle. It may surround a bunch of different cells, but it may not necessarily be surrounding one cell, okay? But the strategy that we thought we might try here is first find a cycle that surrounds many cells. Then try to make that cycle smaller. That's the basic argument we tried. And what we did in order to do that was, the rule we chose was whenever you enter an intersection, choose to leave it around the first intersection you can leave going clockwise. Now, if you follow that rule every time, you will cycle. And now the idea is, if it doesn't surround a single cell, then reverse the rule, start from one edge and now do the opposite rule. And the claim is under certain situations, it will actually form a smaller cycle that surrounds a smaller number of cells. And now reverse, 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 reverse. If you do it carefully, I'm hand waving over lots of small issues, you will end up making this cluster of cells smaller and smaller and smaller. And if you ever get a situation where you can't, that doesn't make it smaller and smaller, then there's some other move you can make to make it smaller. I'm not going to go into that, but that's what this last picture shows. Okay, so there's a strategy, and actually this shows us a little bit about something about how you do math often, is like, okay, you have an idea, maybe it works, and maybe it doesn't work, you have to modify. That's kind of what happened here. We said this idea, oh, it actually works, and when it doesn't, there's something else that'll work. Okay, so that was the first proof, which actually appeared in this paper that just came out recently. But more recently, I had a student who worked on this problem and actually came up with a simpler, much cleaner proof. Okay, her name is Savannah. And the insight here is that this board is kind of like what's called a vector field. Some of you may not be familiar with that, and that's okay. It's just, if you think about wind blowing across the Earth's surface, that's a vector at every direction. It's an arrow at every direction, at every point. That's called a vector field. Here you have a graph with an arrow at every dot, okay? And it's very much like a vector field. And one of the key ideas of Savannah's argument is, hey, we know something about vector fields on surfaces. There's something called the Poincare-Hopf theorem, which I won't go into here. But if you know some differential equations, you know some topology, it might be familiar to those who have some advanced math. But Savannah's insight was maybe the discrete, you can think of this graph as a discrete vector field whenever every edge is marked. And is there a similar theorem to this theorem, whatever it is, that will work in this context? And this is actually one of the things I do in my research often, is I take a continuous idea and find the discrete analog. So here, I'm just going to give you a sketch, literally a sketch of Savannah's proof. Savannah's actually holding up a sketch, a literal sketch of her argument. But here's the idea. If you take a street, you take a city with all the intersections, no stupid intersections, all one-way streets, you can assign to every block a number. We'll call that an index. And the number is the number of times the direction changes as you go around the block. Okay, so count the number of times it changes and then divide by 2 and subtract from 1. That's the index. Okay, so here, no direction changes, the index is 1. Here, the direction changed once as you go around, actually twice, because you switch clockwise, counterclockwise. Let's see, how many times they go around? Switch, 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 switch. Okay, so this actually goes around. Yeah, so this direction switched 4 times. So 1 minus 4 over 2 is minus 1. Okay. Here, the direction changed twice, and so this index is 0. The number of direction changes has to be even, so this number will always be an integer. But you see, the only time the index is positive is if there's no direction changes. That's the important point. Otherwise, it's 0 or negative. Are you with me? Now, to every intersection, you can also assign an index. And again, this is the number of times the direction changes in or out as you go around in one direction or the other. And you just subtract, divide by 2, subtract from 1. So if it's a sink or a source, there's no direction changes, the index is 1. And in every other instance, the index is 0 or negative. Okay? Okay, so the index captures a number of direction changes around each cells or intersection. And you can prove, using induction if you want, that the sum of the indices in any graph, fix a graph, the sum of the indices across this board with every edge marked, sum of the indices is constant. And surprise, the constant is 1. So if the sum of the indices is 1, at least one block or one dot must have a positive index if the sum is 1. But because we rule out sources and sinks, you can't have a positive index intersection. So there has to be a cycle sum. That was basically Samantha's argument. So that's kind of a nifty argument. And it provided a cleaner, in some ways cleaner, maybe more, I mean, requires some work to show all the stuff about indices, but it suggests an interesting structure that underlies what's happening here. Okay, that's just kind of summarizing what I said. All right, so that's the basic two different proofs now that we have of this thing, and that leaves many questions available that you could ask. And I see many of you have lots of questions here. I haven't been able to follow the chat so easily, so we'll have now some time for Q&A. But I'll end with several open questions that may be worth thinking about. So one, someone mentioned earlier in the chat, is you could change the rules of the game, and we don't know what happens often in those instances. Okay, how do you play the game with more than 3 people? There's another interesting question, because whenever you have more than 2 players, there's a chance for players to collude, right? So you have to worry a little bit about some of the cooperative and non-cooperative aspects of the game. You might change the game with a different goal, right? It might be get as many cycle cells as possible. That's a completely different game. You might change the kind of board. And that, I've only told you about 2 kinds of boards that we know the answers to, but I know a few other classes of boards that we have some answers to how to play, but there isn't a general theorem yet. So for instance, if you have a board with 2 polygonal cells and 1 common edge, we know how to play that game. But if it has more than 1 common edge between the 2 cells, we don't know how to play that game. So that's unsolved currently. If you have a game that looks like this a multi-story house, this is a game with a reflective symmetry, but notice it has several edges crossing the axis of symmetry. We don't know how to play that game. I recently, somebody sent me an email saying they know how to play a 2-story house, but in general, we don't know who wins that game. So there's an interesting open question. And is there some way to actually look at a board and break it up and somehow tell whether, in general, for the general board, whether player 1 or player 2 has a winning strategy? There's an interesting question. I haven't gone into this at all because it involves higher level math, but you could also imagine this game being played on other boards that aren't just the plane. So you could play it on a 2-dimensional surface. You could play it on an arbitrary cell complex, whatever that is. And I can tell you about that if someone asks. Lots of open questions here, and maybe you have some. So I'll end here and leave some time for questions.
Great. Thanks so much. So yeah, ask questions. You probably have a lot of them, just like in the other talks.
I will, I'm looking through the past chat. Just raise your hand if you have a question. I'm looking through the chat just to see if there are questions I haven't answered. One person, Jin Fei, asked, what if there are multiple edges crossing the axis of symmetry? Yeah, we don't know the answer to that question in general. Sometimes those games are covered by prior, some of the other, like if instead of a two-story house, you just had a ladder, then that, even though you could consider a ladder a game with reflective symmetry, you could also consider a ladder as a game with rotational symmetry. And under rotational symmetry, that game actually, we know how to play that game using the rotational version. So that's why a two-story house is more interesting, because it does not have 180-degree symmetry. And so it can't be answered by the 180-degree theorem. Another question earlier in the chat was, could you explain symmetric board in a more graph theoretic way instead of using a drawing? Interesting question. Would whoever asked that question be willing to explain what you mean by more graph theoretic way? I'll try to interpret the way I think. So I guess the way to do it carefully, I'm not sure if you mean more graph theoretic, but instead of using a picture, but if you mean more carefully, the way to define it is to talk about a group action on a graph, and the group action is basically a symmetry of the graph. And what we're talking about here is a symmetry that has order 2, meaning if you do it twice, well, if you do it once, the graph the graph stays the same, though edges get moved around. But if you do it twice, every edge and every dot comes back to itself. So I'm not sure if that's what you mean with graph theoretic, but you probably need to appeal to a notion of a group action or symmetry. I see there's several new messages now. Oh, okay, great. Some great questions here. Why are people interested in game theory? Yeah, good question. So certainly the kind of game we've been playing is what's called a combinatorial game. So it's just like a game that, like a parlor game that you're playing and you want to know who wins. Game theory in general, you can think of as the mathematical modeling of decisions and decision making. This area of math actually grew out of World War II. Just after the war, during World War II and after the war, many mathematicians were thinking about games of strategy. And game theory actually asks you, when you think about agents interacting in some way, what's the best strategy in order to win? And so often these kinds of games, even though they might seem very simple, can be, when put in a framework, can be used often to explain, for instance, why, Germany was split into 4 pieces, after World War II. Like, what was the strategic, sometimes you can set up what are called game trees that allow you to think a little bit more analytically about why certain decisions, people make certain decisions, or to prescribe how people should play a particular, behave in a certain situation, right? So game theory often has, a prescriptive, a reason people might say is because it's prescriptive, it tells people how to play, or it's predictive, it might predict how play is going to go, or it's descriptive, it might tell you how to look at a past situation and explain why that situation happened the way it did. So it does have broader uses, and often, what you're looking at are games on trees. That's a great question. Let's see, another question. Is player mirror reverse on a graph with symmetry analogous to playing 2 piles of equal size in NIM? Okay, this is a great question. It brings up actually a larger question. So this game is an impartial game, and there's a theorem called the Sprague-Grundy theorem that says certain kinds of 2-player impartial games of perfect information, whatever that means, actually are equivalent to certain kinds of NIM games. For those of you who know what NIM is, but if you don't, not a big deal. But there's a theorem that says there are certain equivalents. That is, if we know how to play one game, you know who wins one game, you know who wins the other. You could analyze this game using the Sprague-Grundy theorem. But one of the things that's less satisfying about that is that Sprague-Grundy doesn't give you a way of thinking about, like, what I want to know is, as a human being, if I'm playing this game, I don't want to have to resort to some theorem or computational thing over here to tell me how to play. I want to understand how to play this game. So while Sprague-Grundy could offer a way of deciding who has a winning strategy and maybe allow you to compute it in some, in some way, it's not going to be efficient. It's not going to be understandable. And so here we are thinking about this as what we want to know is there an understandable strategy? Are there other strategies that always work on some boards? Yeah, we didn't talk about this, but we do know how to play certain other games. They are mentioned in this paper that's on the screen. If you want to read about it, you can probably find this also in the archive online. There aren't that many boards we understand how to play, but yes. What does Poincare-Hopf theorem say? That's a great question. So the Poincare-Hopf theorem says the following, and maybe this is a little surprising to you. So here's one way of thinking about it. Here's a question, think about the Earth's surface. And now think about the wind blowing on the Earth's surface. And the question I'm going to ask you is it possible for the wind to be blowing everywhere on the Earth's surface? How many of you say yes? How many of you say no?
But isn't it impossible because wind is caused by a difference in air pressure? If wind's blowing everywhere, then it wouldn't make sense for there to be like a difference in air pressure at all places on Earth.
Yeah. Oh, so let me say it a different way. I guess what I mean is wind blowing continuously on the Earth's surface. I guess I'm not thinking about this in terms of pressure. I'm just thinking about this. Is it possible to put a vector on the surface of the Earth in such a way that nearby, on every point of the Earth's surface, in such a way that nearby points have wind blowing in nearby directions? That's a question. So here's a thing you might think about. For instance, if I have the wind always blowing east on the Earth's surface, what you realize is that actually that means at the North Pole and South Pole, the wind is not blowing. Okay. So the Poincare-Hopf theorem says something interesting. It basically says on the Earth's surface, there always have to be, I'm going to put this in quotes, 2 points on the Earth's surface where the wind's not blowing, if you're talking about wind blowing continuously. Now, the reason I put 2 in quotes is that it's possible to push those places where the wind's not blowing together in some interesting way. But that means that what's happening just outside those points, the wind is doing some weird stuff. Okay. And so what the Poincare-Hopf theorem says is it says assigns to every 0 in a vector field, every point where the vector field is 0, an index, and that index takes into account how the wind pattern is just outside the 0. And that's very similar to what Savannah did with dots on a graph. It sort of looks at, I can't go into it on Zoom, but it sort of looks at what's happening locally and assigns an index. And the Poincare-Hopf theorem says that index must be a certain fixed number, and that number turns out to be what's called the Euler characteristic of the surface. So if you've heard of the Euler characteristic, great. If you haven't, don't worry about it, but you can learn about it. It's a topological number that you can assign to every surface that somehow characterizes a surface. And what's surprising here is that the index is the Euler characteristic. Okay, that's kind of pointing at some things which may intrigue you and worth learning about. Where can we find Savannah's proof? Yeah, so good question. So Savannah's thesis, well, we're still writing this up. We're going to write it up in paper form, and it's not posted yet or public yet. Are we still working on this problem? Yeah, good question. There's lots of aspects of this problem. So since the paper came out, several people have written me saying they're looking at various different aspects or questions, different boards, different questions. We're still working on some questions, which could be the subject of another talk. But yeah, there are lots of questions here to explore. Is the Euler heuristic that thing like v minus e plus f equals 2? Yes, it is. So here's one way to think about this. If you put a board on a sphere, so v minus e plus f equals 2 on a sphere. And that number 2 also reflects what happens if you play the board on a sphere. So if you play a board that's on a sphere, then the outside cell, the one that's on the outside, if you count that as a cell, then a winning move would be a cycle that goes all around the boundary. If you allow that as a winning move, that's counting the outside as a cell. That's an example of a in that case, what will have to happen is there have to be 2 cycle cells whenever you fill out the whole board. Lots of great questions. But that may be all the questions. Oh, here's another one. Are there strategies that predict winning cycles for asymmetric games? Yeah, so I had a student who worked on a project, a senior thesis project, where if you had a board that could be broken up into symmetric pieces in certain ways, then in fact, they had a way of deciding who wins that game. It's maybe too complicated to describe here, but it involved basically breaking the board into pieces that were symmetric. So that's kind of what I was referring to in my last slide about decomposition theorem. Like, could you break a board that you don't know how to play into pieces that you do know how to play, and as a result, play the whole board? But that has to be handled very delicately. And in this situation, the pieces were all connected, by vertices or edges in certain ways. Yeah, so the fundamentals of winning strategies would still be symmetry. Well, that's what we were able to do in this instance. I don't know that that's always the case, but maybe you could come up with some other way of deciding who wins. Now, the Sprague-Grundy theorem would allow you to compute who wins, and it's just not clear at the end that you've learned very much about about how to play games. Yeah, I mean, who wants to code the pieces into a computational machine and have it crank out who wins, right? Like, not clear that that's the way you want to think about the game. Oh, what's the event we met at? So after Chris and I played this game and discovered a few things about a few simple boards by correspondence, I was invited to lead a research group at ICERM. And the idea there was to come together for a week, think about a few problems, and make progress on the problem. And this seemed to me to be an ideal kind of question where some progress could be made. And so that's what we did. It was called the REUF program at ICERM. That basically means research experiences for undergraduate faculty. All right. I'm guessing that's the last of the questions. So thank you very much for coming to the talk, and I guess I'll turn it back over to Simon.
Okay, thank you so much. So let's end this part of the class and move on to the next part now.